So hi everyone, thanks for coming out to a special edition of our weekly LDRD Carbon Cycle 2.0 seminar series. We've kind of decided that it's been a while since the lab audience has heard updates of the research areas that are involved in Carbon Cycle 2.0. So we've started to insert, when we have speakers available, updates on the research areas that are involved in Carbon Cycle 2.0. You remember the diagram that we've all seen Paul present with the research bubble areas. So today we'll be hearing about Earth's carbon cycle, sort of a general Earth sciences update on carbon cycle research at the lab. We'll resume the LDRD series next Thursday at 2 in the Building 15 auditorium space. So today we'll be hearing from Don DePaolo, who's the Earth Sciences Division Director and also the ALD for Energy and Environment at the lab. So I'll hand it off to Don. Oh, and just a reminder, since we're webcasting today's presentation, for questions at the end, please wait for either Sandy or myself to come to you with the microphone so we can capture that on the webcast.
Great. Thank you, Melissa. Is this about the right volume, or should I move down slightly? Maybe a little bit. Okay. Thanks very much. The purpose of this talk really is to back off with regard to the carbon cycle from the parts of it that we normally think about here with regard to carbon cycle 2.0, and also in terms of what we normally are thinking about in terms of climate change and what might be happening in the next couple of hundred years, and take a sort of planetary scale view of carbon so we can look a little bit at what we're doing now and how it compares to what's normally happening on the planet. And I think it gives us a sort of special perspective on the sort of magnitude of the changes that have happened recently. So I'm not going to be talking a whole lot about things like evidence for the change in the Earth's temperature and that sort of thing. Ultimately, all of that comes from the way carbon is moved around on the planet. So I sort of want to focus on the carbon cycles themselves, and again, on a pretty large-scale view. So the outline in the form of questions are, what are the major carbon reservoirs of the Earth? Where's most of the carbon? And then how fast does carbon normally move between these different areas? And what's the evidence for how fast it moves? Then there's the role of water. Now, it turns out that water is like a magic component because it's present at the Earth's surface. The Earth can do certain things that other planets can't. And Venus is a very nice counterexample in comparison to the Earth, which shows what happens when you have a planet that's in a situation where it doesn't have liquid water at its surface. Then I want to talk briefly about rock weathering, because on the long time scales of the Earth, it's the weathering of rocks, or what we call weathering of rocks, and I'll define that, that effectively is the mechanism by which carbon can be removed from the atmosphere and stuffed back into the Earth in places where it won't affect climate. Now, and then finally, I'll get to the end. What about fossil fuel burning? How big an effect is that in comparison to the natural system, and or the implications of that? So you've seen this diagram before. This is our carbon cycle 1.0 diagram, which represents the sort of pre-industrial carbon cycle. And I think what this shows is that there's big arrows here where carbon moves back and forth between different parts of the near surface system of the Earth. But there's really only one arrow that represents carbon being transferred from deep Earth reservoirs, like sedimentary rocks, or even deeper in the Earth's mantle, up into the atmosphere, and that's fundamentally volcanism and things that are related to volcanism, so various other thermal areas on the Earth, and even in fault zones like the San Andreas Fault. Matt Kennedy, I see back there, has shown evidence in a nice science paper several years ago where there's CO2 from the mantle leaking up through the San Andreas Fault. So when you add up all those fluxes, they come out to a number that's about something like 0.1 or 0.2 gigatons of carbon per year. And what we'll come back to at the end is that the current flux due to fossil fuel burning, which effectively is the same kind of thing. It's taking carbon from where it normally is stored for long periods of time and injecting it into the atmosphere, that number is approaching 10 now for the fossil fuel burning plus land use change. And ultimately, I want to make the conclusion that I don't think there's much uncertainty in telling the number 10 from the number 0.15. Okay. There may be other areas of uncertainty, but I don't think that's uncertain. Okay. So here are some other things that are going to come up. The essential characteristic of the Earth, as I mentioned, is that it has liquid water at its surface. And as far as we can tell, that's been the case since about 4.4 billion years ago, which is not that long after the Earth originally formed. So for a long period of time, the surface temperature of the Earth and the surface conditions have not been all that much different than they are today. It's amazing when you see what's been going on. So the carbon cycle is what apparently regulates the surface temperature. It's the amount of CO2 essentially in the atmosphere. It can be changed by adding methane or other greenhouse gases, but effectively CO2 is the major driver of this. And because of the fact that the Earth has this carbon cycle that regulates the atmospheric concentration of CO2, it's maintained the Earth's surface temperature in a rather narrow range for a very long period of time, which I think, has something to do with why very high forms of life have been able to evolve. One of the things that's most amazing is that the carbon cycle has been able to almost exactly compensate for the fact that the sun has gotten brighter over the last 4.4 billion years by about 40%. So this 40% number is, if you compare the original value of the luminosity of the sun to the present value is about 40% larger. But when you turn it around, the original sun was about 30% less bright than it is now. This corresponds to a factor of 1,000 in the CO2 concentration to make up for that difference. Interestingly, the presence of liquid water on the surface also changes the way the interior of the planet works. And so we have this thing that geologists discovered in the 1960s and 70s called plate tectonics, where relatively rigid surface plates at subduction zones actually go back down into the mantle. And we believe that this occurs because of the presence of water, that water causes a certain amount of weakening of the upper mantle right below the crust and causes this a rather large contrast in the sort of character of the rock. So just below the plates, the rocks are pretty fluid and the plates are very stiff. And this is probably a fact that comes from the presence of water. This allows the plates actually to get bent and go back down into the mantle. And this is a mechanism for taking carbon that has come up to the surface of the Earth and stuffing it back down deep into the Earth. This is another thing that Venus can't do. Okay, we'll go through this in a minute. The Earth's atmosphere contains a very small part of the accessible carbon on the planet, about a ppm of the carbon. And it's important that that be regulated. If you change it to 2 or 3 ppm, changes the temperature by a lot. And I already mentioned this. And the other thing that I'll mention is that if we continue to pump carbon into the atmosphere at the current rate for long enough, we'll create an effect that won't go away for about 100,000 years. Okay, so let's go back. So the initial point was, when did the Earth sort of reach this stage where the conditions on the surface were not so much different from the present? If you go back 30 years or so, geologists and planetary scientists used to argue about whether the Earth started out as a cold piece of rock, which then heated up due to radioactive elements in the interior, or whether it started out hot due to the gravitational energy that was deposited during the growth of the planet from smaller pieces. This whole idea has now been superseded by the idea that late in the history of the formation of the Earth was struck by a Mars-sized object. And people have done now some simulations of the energy and sort of kinetics of energy balance and kinetics of that kind of impact. And if you hit the Earth with a Mars-sized object at about the right angle, you end up with this series of, there's been a number of, you can look up these movies on the web. And the bottom line is it deposits enough energy in the Earth. So if you look at this last one here, this is the initial part of the impact, and then you see a whole lot of the Earth has been torn off here, and it includes part of the impactor that goes out here, and you get this trail, and then you also see that there's a little thing starting to form here, a little nucleus that eventually becomes the moon. So that's the way the moon formed. The original problem was, why does the Earth have such a big moon? The only other planets in the solar system that have big moons are way out there. They're Jupiter and Saturn. The other planets that are close to the sun, like Venus, has no moons. Mars has a couple of moons, but they're just little chunks of rock that it captured. They're meteorites, or from the asteroid zone. And Mercury, of course, doesn't have any moons. So Earth has this big moon, and there was this question, why should it have a big moon? This seems to be the answer. And the corollary is, you can't read the temperature scale here, but the red is about 10 to the 7th degrees centigrade. So the idea is that this impact completely melted the Earth, essentially. So the Earth's now initial state was not at the very early time of the solar system, but about 40 million years later when this impact happened, which melted the whole thing and formed the moon. So there's no longer any argument about whether the Earth started hot or cold. It started hot, and when it started was a little bit later than we originally thought. This diagram shows a time scale. This is time since the oldest objects in the solar system, which are these little calcium aluminum rich inclusions that are found in certain meteorites, which have been dated to be 4,567 million years old. And it turns out that they're pretty much the age of the solar system, because the total amount of time that it takes for a gas cloud to collapse to start to form a star is only a fraction of a million years. And then after that happens, you start to get these solid bodies forming. And that whole time scale is pretty short. So we pretty much know that the solar system formed at about this time, 4,567 or 8 million years ago. But it took 40 million years after that is about when or even maybe a little bit later, is when the moon forming impact occurred. And coincidentally, the sun took about that long to self-compress enough so that it was hot and dense enough in the center to start fusion reactions. And so at about the time the Earth was reset by this impact, the sun also became effectively a star. Okay. This is an artist depiction that I found on the web. I can't find it anymore. I found it a few years ago, of the Earth about, a few hundred years after the moon forming impact. It has liquid rock at the surface. It actually has vapor silicate in the atmosphere. So the first rainstorm on the Earth after this was silicate rain coming out of the atmosphere at a very high rate, like several meters per year. And then once that happens and you get all the silicate out, you're left with gas in the atmosphere. And then the Earth stays really hot until you form a crust on it. As soon as you form a crust, then you have to transport heat by thermal diffusion through it, and it cools off quite a bit. And then the water vapor in the atmosphere can actually start to condense, and you start to get liquid water at the surface pretty soon after that. And then you get up to the point, not quite, but still takes a while after that, where you can start to have something that looks a little bit more like a planet like we have today, except that virtually all the carbon that the planet had gets degassed during this liquid stage, and it's all in the atmosphere. So you've got an atmosphere that's full of all of the Earth's carbon, which is a lot of carbon, and which means that it's going to have an enormous greenhouse effect, and it's going to be pretty warm. And step one in the carbon cycle is how to get that carbon out of the atmosphere and back into the planet. And so there's a very interesting set of papers written by Norm Sleep and Kevin Zonley over at Stanford and Ames on how this might have worked. And this was the first version of the weathering cycle, and the first stage was to get all that carbon back inside the planet. Now, if we go now to the evidence for the early Earth being not so different from the present, one of the things that we have is we have sedimentary rocks that look like they form in a sort of oceanic environment that was not much different than the current oceans, that are almost 4 billion years old. And in fact, this particular picture is rocks that are 3.84 billion years old, but there are some that are a little bit older than that, pushing about 4. And then there are single mineral grains of zircon. Now, zircon is a zirconium silicate, which has a fair amount of uranium usually that's incorporated into it, and the uranium allows it to be dated very precisely. Now, zircons have this interesting characteristic that they dissolve at about a near zero rate. So they're indestructible once they're formed in igneous rocks. And so they tend to get formed, in sandstones, like sand grains are mostly made up of quartz, but you can usually find some zircon in there. And if you make that into a rock and put it in a mountain range and then erode it again, the zircons just keep getting recycled because they never go away. And so people have found that in certain parts of the Earth where there are already old rocks, they've been able to find zircons that are even older than the rocks. And the oldest zircons have been found to be about 4.4 billion years old, which is now only about 150 million years since the moon-forming impact. And those zircons have isotopic characteristics. So one of the elements in the zircon is oxygen. Turns out if you measure the oxygen isotope composition of these zircons, they indicate that they came from granites that are not much different than you might find in the Sierra Nevada. And the petrologists think that you can't form those granites unless you have a lot of water around. And consequently, this is evidence that there was liquid water at the Earth's surface all the way back to 4.4 billion years ago. So this evidence comes from the secondary ion mass spectrometry technique, where people have been able to figure out how to measure the ages of these little spots on these small minerals to very high precision. Okay, so we'll come back to this issue, and this is a cover of a magazine from a few years back showing what the early Earth might have looked like, and you see there's a lot of volcanoes, but there's also oceans. And the moon is out here, and it's not as far away as it is now because it's been gradually receding. Okay, so where's the carbon? So when people talk about carbon, they like to talk about gigatons of carbon. These are metric tons. The Earth, we know the mass of the Earth pretty well. It's about 6 times 10 to the 12th gigatons total mass. The mass of the atmosphere is not very big. So these are 6 orders of magnitude smaller, and you figure that carbon's not very much of the atmosphere. So the total amount of carbon really isn't that much that's in the atmosphere. And of course, it has this liquid water. This diagram, which comes from a textbook that came from Princeton Press, is very nice because it shows a lot of things to scale. It shows the subduction zone here on the west coast of North America, and another one here at the Peru-Chile area, and another one over here in the Tonga area in the western Pacific. So this shows pieces of the Earth's upper mantle and crust diving back down into the mantle. It shows the core down here. It shows these plumes of hot rock that come up from the core mantle boundary. So interestingly, there's various processes that we know about that allow things from the surface to be sent back down into the deep mantle, and that allow things from the deep mantle to be brought back up to the surface, like Hawaii over here is an example of a mantle plume. So we have ways, if we're clever enough, to sort of tell what's going on at various levels of the mantle. Okay, so most of the carbon in the Earth is in the areas that we don't usually worry about for the surface carbon cycle. The core of the Earth is made up mostly of iron and nickel, while carbon can alloy with iron nickel at high temperatures as a metal pretty well, and it's estimated that the core has about 0.2% by weight carbon, and we know that it has light elements other than iron and nickel by the seismic properties, and we've always argued about what they are, but the most abundant elements in the solar system, other than iron and nickel that are likely to be down there, are oxygen, carbon, and sulfur, for instance. And so people have always been partial to those 3 elements being the light elements in the core. And so carbon's probably about 0.2%. So that turns out to be 4 times 10 to the 9th gigatons of carbon. And that's where 90% of the Earth's carbon is. But that carbon is essentially not accessible to the surface. There's very little chance it'll ever get to the surface. The mantle is the next biggest place, and it's down by about an order of magnitude. And this number is uncertain by at least a factor of 2, but it's about roughly 4 times 10 to the 8th gigatons. This is assuming that the average concentration of carbon in mantle rocks is about 100 ppm. It might be 50, but it's somewhere in that area. This carbon is actually accessible to the surface. It's very likely that almost all the carbon that's in the mantle today has been exhaled into the atmosphere by volcanoes and stuffed back down in the mantle at least once. Okay, I'll show you why in a minute. So the next biggest reservoir is the actual continents and the sediments that are lying on the ocean floor, and they're down by another order of magnitude, about 8 times 10 to the 7 gigatons of carbon. We'll come back to this number in a minute. Okay, so the other ones that I have in the other color here are the parts of the carbon cycle that we talk about most these days. So the atmosphere in the pre-industrial era had about 600 gigatons carbon in it. It's now approaching 800 gigatons carbon because we've increased the concentration. The land biosphere is on the order of 600 gigatons carbon. You'll see different numbers for this in different sources. Soil, depending on how you count it, is about 1,500 gigatons. Maybe this could be off. Could be bigger than this number, but it's sort of in the 1,000 gigaton, couple thousand gigaton range. The deep ocean has a lot of carbon in it, 38,000 gigatons. The surface ocean, which is the part that interacts rapidly with the other parts here, has about 1,000 gigatons. The reservoirs that we're concerned about are the fact that there's about 5,000 gigatons of coal that we figure we could find if we put our minds to it, and if we figured out a way to develop methane hydrates from the ocean surface, that might double that number. So if we were really bad people and decided to burn all of this carbon and put it into the atmosphere, CO2, that's 10,000 gigatons of carbon, and you can compare that to what the normal system is handling, which is about 3,000 or 4,000 gigatons. So that's a big effect. We'd be multiplying it by a factor of 3 or 4. Okay, so this issue of carbon coming out of the mantle. Where's the evidence? Well, here's a nice example. This is a map of Hawaii. This shows the Kilauea volcano when it was in active eruption. It stopped erupting earlier this year, but it erupted continuously from 1983 to 2011. About 3 gigatons per year of lava was coming out, and that represented about 10 to the minus 3 gigatons of carbon per year. And here you can see the plume. Here you can see the, back when Pu'u'o'o, the vent was fountaining, you can see the gas coming off of the lava as it comes to the surface. At high pressures, the gas is kept in solution in the magma. As soon as it comes out to the surface, it bubbles out and goes into the atmosphere. And this is not just CO2, it's also water and SO2. And in fact, you can also see that this plume sort of gets carried down here and then around the island. And the Kona area of the Big Island is over here, and that's where most of the people live, and they actually have pretty serious health effects from the SO2 that gets blown around here. And some of this actually trails down to the other islands, and they have smog, or what they call VOG, from the volcano that affects weather farther down the chain. Anyway, this is the sort of order of magnitude of a relatively large volcano. And the total flux from volcanoes is probably about 100 times that if you average it over the whole Earth. That puts you up at about 0.1, and then if you sort of take account of all the other places that carbon's leaking out, it might make it 0.2. There's a recent paper on this that has come out in, I forget which magazine, but it's still a little bit uncertain exactly what this number is. If you sort of think about all the places where volcanism is going on. So all these red dots here on the map are active volcanoes. All of the black ridges here are active volcanoes too. But the way carbon behaves when it's erupted from submarine environments is different from where it's erupted directly from volcanoes on land. And in fact, most people think that the carbon that comes out of the submarine volcanoes is canceled out by carbonate that forms in secondary veins in the oceanic crust. So if this sounds like hocus pocus to you, that's good, because somebody should do some further research on this and whether or not this is actually an exact balance. But if you add up all these volcanoes, this outgassing rate comes out to be about 0.15 gigatons of carbon per year. So you have to multiply that number by 3 2/3 if you want to get gigatons of CO2. And so, that's much bigger than this anthropogenic number. But what's interesting about this number, if you take that number and you take the total amount of carbon in the mantle and you make this division, this gives you the amount of time it takes to exhale all of the carbon in the whole mantle. And it's a number that's about half the age of the Earth. So what this tells you is that a planet it's possible to transfer all the carbon from the mantle into the atmosphere and accumulate it all there if you don't have a way to take it out and put it back in somewhere. And another interesting number that I haven't heard people talk about very much, if you take all of the carbon that's in the Earth's crust, which is about 8 times 10 to the 7, and divide by this number, you get a number that's only about 1/10 of the age of the Earth. So that means that carbon is moving up to the surface, being incorporated into rocks, and then shoved back down into the Earth on a very rapid time scale in a geologic sense. Okay, so do we have any other evidence that really this kind of thing happens, that you can get all the carbon out into the atmosphere? Well, yes, this has happened on Venus. So on Venus, the atmospheric carbon is about 50% of what I would call the accessible carbon. So the amount of carbon in the Venusian atmosphere, which was 2 times 10 to the 8th gigatons, is about half the value that we've assigned to the mantle on the Earth. It might even be the whole value. So Venus is a case where virtually all the carbon's been transferred from the mantle into the atmosphere, and it's all accumulated there, and because there's no way to return it back down into the mantle. The Earth has probably outgassed just as much carbon by volcanoes, but has been able to stuff it back in and keep the amount that's in the atmosphere at a relatively low number. So this is the comparison. Present day is 800, it used to be 600 versus 2 times 10 to the 8th. Okay, so there's an interesting sidelight here about why Venus, didn't fare so well. By the way, Venus has active volcanism today still. The various landers and orbiters that have gone there have been able to take enough pictures in various wavelengths to see volcanic features on the surface that look very young, and there's evidence from the gas composition of the atmosphere that there have been eruptions in the last few decades. Okay. So part of the reason Venus has a problem is that it's too close to the sun. It's too close to keep it from having a strong greenhouse effect, a greenhouse effect that's so strong that all the water that would be at the surface evaporates and is in the atmosphere. So if you've got carbon and water coming out of the Earth's or the planetary mantle and accumulating in the atmosphere, in the upper part of the atmosphere, due to the solar energy and X-rays from the sun and also the solar wind, you ionize, you dissociate the water into hydrogen and oxygen, you ionize the oxygen, the hydrogen gets entrained in the solar wind and basically gets stripped off the planet. And it can be done fast enough that as you degas the water from the deep mantle, you strip off the hydrogen, and you're only left with the oxygen, which then combines mostly with carbon in the end and produces CO2. So Venus just had the unfortunate situation of being a little bit too close to the sun. However, one of the interesting things that people are pursuing now is the sort of thought experiment. Venus is too close to the sun now, but the sun is a lot more luminous than it used to be. So if you think about what Venus was like when the solar system was young and the Earth and the sun was not so luminous, it's possible that Venus was more like the Earth, say 3.5, 4 billion years ago, because the sun wasn't so bright. It might have had water at the surface, and it might even have had plate tectonics and so on. Anyway, the Earth, of course, is totally different because all of the water that comes out of the Earth's mantle that accumulates at the surface ends up in liquid form at the surface in the oceans, and very, very little of it, about 1 part in 10 to the 5th, is in the upper atmosphere. So you can ionize a little bit of that, but you can take it away in the solar wind, but so little of it is up there that you can't get rid of much of it. So the Earth basically has this abundant water, at the surface. It allows it then to keep its water in the liquid state, and then that eventually will allow it to help to recycle the carbon, which I'll talk about in a minute. Okay, so this is the diagram. It's a little bit complicated, but in case you were wondering what the sun was doing, these are the models. If this is the time since the origin of the solar system, this is the luminosity of the sun relative to the present, which would be 1. And so it started out pretty hot, then it got cold, or not so bright, then it brightened up a little bit. And then when it settled in, about 100 million years after it started forming, it was about 70% of the present value, and since then it's drifted up like this. You can also see that the solar wind and the X-rays and UV were much stronger in the past than they are today. So this stripping process in the upper atmosphere was more effective early on in the solar system history. So if you put all of this together, Jim Casting from Penn State has written a couple of papers on this and come up with this concept of the habitable zone, HZ, which is generalizable to other star systems or planetary systems. So depending on how big the star is, so this is the mass of the star relative to the sun would be plotted at 1. If the star is small, it's not so bright and luminous, and you can afford to have planets that are closer to it and still be cool enough at the surface to have liquid water. If the star is bigger, you have to have the planets be farther away. So this is what he's calculated to be the habitable zone. This is where the planets are in the solar system. Here's Earth. Here's Venus. It's just a little sort of too far on the edge of the habitable zone. Here's Mars. It's a little too far on the other side. And this moves a bit with time. I think with time, as the star brightens up, it moves from the left to the right. And then there's some other things plotted on here, like the tidal lock radius, which means that if you're too close to the star, your planet doesn't rotate because there's too much of a gravitational pull, and one side of the planet is always facing the star. And presumably that's not good for sort of modulating the surface temperature very well. So anyway, this has been generalized, and this is one of the concepts that's used when people are planet hunting to sort of assess whether the surface conditions will be similar. One other sort of interesting fact is that Venus actually absorbs less energy from the sun than the Earth does, but nevertheless, its surface temperature is way higher than the sun. So the incoming solar radiation at Venus is about 645 watts per meter squared. On Earth, it's about half that. Venus, though, reflects back, almost 80% of the light, and the Earth reflects back only about 30%. So you sort of know this. Venus is pretty bright when you see it in the early evening sky, but it's the difference between the upper atmosphere and the surface temperature that really determines what the surface temperature is going to be. That's kind of the definition of the greenhouse effect. That's huge on Venus. The upper atmosphere looks like it's 285 degrees C, and the lower atmosphere is, the surface temperature is 460. However, if you go back far enough, the solar radiation back in the early days was probably not that low, but at Venus it might have been down around 450 watts per meter squared, and Venus might have been different back then. Okay, so this demonstrates that carbon gets out into the atmosphere. How do you get rid of it? And the idea is this climate regulating carbon cycle. So the CO2 is degassed from the deep Earth. It's added to the atmosphere. Once it gets in the atmosphere, it combines with whatever water it's in contact with, the oceans or clouds, and forms carbonic acid. So the CO2 is then removed from the atmosphere by a reaction of this carbonic acid with silicate minerals, which have to be then exposed at the surface, and eventually it's fixed in limestone. And when you write this as a bunch of chemical reactions, first you dissolve the CO2 into water and you produce an acid, a weak acid. Then you take these hydrogen ions, you react them with silicate minerals that have cations like calcium in them, and what you end up doing is releasing the calcium and forming a mineral that's hydroxylated. which means that the hydrogens that are over here end up in the solid form as hydroxyls, and you've essentially then returned to the ocean the leftover HCO3 and the calcium ions. And when you add up this whole thing, you end up taking CO2 and combining it with a silicate mineral, producing a clay mineral and calcium carbonate, which is a solid, which accumulates on the ocean floor. So this is the mechanism that chemically by which carbon is taken out of the atmosphere. Well, let's look at this diagram of the Earth and see whether we can understand this a little bit better graphically. So this is kind of a simplified Earth. There's a continent here where the crust is pretty thick, mountains stick up. There's an oceanic crust, and it dives down into the mantle in some areas, and there's usually volcanism associated with that. And so, and then down here is the mantle, up here is the atmosphere. So step one is the CO2 is being released from the mantle by volcanoes. This also happens on the continents over here, but I didn't want to make it too complicated. That CO2 then dissolves in the ocean, and that then acidifies the ocean. So if you had nothing else going on, you'd pump CO2 into the atmosphere, that CO2 would continue to dissolve into the ocean until it reached equilibrium. You'd have a pretty acidic ocean and a lot of CO2 in the atmosphere. However, the CO2 in the atmosphere also produces kind of acid rain, and that acid rain then reacts with the rocks that are exposed at the surface of the Earth, partially dissolves that rock, and that tends to deacidify the oceans. So this is the thing that tends, this makes is the source of acid, this is the source of base, and together they can keep the ocean kind of neutral as long as you're continuing to do the weathering and precipitation of calcium carbonate. And then the Earth has this additional little feature that subduction provides a mechanism to take the carbon that's lying on the ocean floor and stuff it back down into the deep mantle. Okay, now the idea of dissolving rocks is kind of an interesting thing. So we do it in various ways. If you, those of us who study rocks have dissolved them in our laboratories. If you want to dissolve them, you have to use very strong acids, concentrated acids like HF, perchloric, and nitric. You have to crush the rock to a powder so there's enough surface area, and you usually have to heat it up to about 100 degrees C on a hot plate if you want it to dissolve in a couple of days. So you can dissolve rocks, but it's not easy. It also happens in geothermal systems. You can see the evidence like this. This is the Long Valley geothermal system. You see some hot steam coming out from a small geyser. And over here, this white stuff is kaolinite. That's that mineral that's aluminum silicate hydroxylated. It's rock material that used to be volcanic rocks. These are layers of volcanic rocks. It's been completely leached of all of the cations, and it's an hydroxylated aluminosilicate mineral. And that happens on those time scales. If you want to dissolve rocks with carbonic acid, it takes a long time. First of all, most natural fluids like rain have pHs that are close to neutral, and this is a diagram that shows some experimental data on how fast the feldspar albite dissolves in the laboratory. These units are moles per meter squared per second. If you actually look at what typically happens in soils and in subsurface environments, those numbers are about 4 or 5 orders of magnitude lower. If you want to know how slow this is, I tried to do this calculation, and I might have made a mistake, but 10 to the minus 16.5 moles per meter squared per second means that if you had a 0.5 millimeter diameter grain, this rate would mean that it would be dissolving at the rate of 1 molecule per second. So it's like, you know, picking the molecules up with the surface. She loves me not. She loves me. And that would mean that it would take 1,000 years to dissolve a 1 nanometer layer of the surface of this of a mineral grain. So this is really slow. So this process happens. It's of geological interest because in the long term, that's what's regulating the atmospheric composition. But we can't count on this to help us in the near term. It's too slow. So if you think about sort of on a grander scale, here's a picture I took in Tibet, another picture of a road cut in Tibet and some rocks in the eastern Sierra. So you're taking these minerals, you add this weak acid, and very gradually You release these cations that stay in solution in rivers and get carried to the ocean. You end up with quartz grains because quartz doesn't dissolve much at all. You form kaolinite. And you also take carbonate ions back to the ocean in the water as well. And then eventually you combine the calcium with the carbonate ions and you form calcium carbonate, which then helps take the CO2 out of the atmosphere and eventually back into the planet. If you want to ask me about these other elements, I'm going to tell you the story for those other three elements is exceedingly complicated. Magnesium in particular is like totally different than calcium. And sodium and potassium, we know that a lot of sodium accumulates in the ocean. And we have, there's various, we also know that we've got to get rid of it every once in a while. And it's not even clear how that happens. Calcium turns out to be, the simplest story. One thing to keep in mind, if you actually dissolve a carbonate mineral like a limestone and transport that to the ocean, that does nothing with regard to the carbon cycle because you're just moving the calcite from one place to another, and there's no net removal of CO2. If you wanted to make a simple mathematical model or sort of understand how this feedback works that regulates the Earth's surface, I think of it in this way, in this kind of feedback cycle. If you try to increase the CO2 in the atmosphere, then you'll increase the acidity of surface waters, and you'll also increase temperature by the greenhouse effect. Both of those will work in the direction of increasing the weathering rates, the dissolution rates of rocks. That will tend to form calcium carbonate at a greater rate and decrease the CO2. If you try to decrease the CO2 too much, you'll decrease the temperature, you'll deacidify the waters, slow down the weathering, and allow the CO2 to go back up again. So it's this cycle that sort of tends to drive the CO2 to a narrow range, but this is very simplified, and we don't know exactly how this, when it's at steady state or when it's not. If it gets driven out of steady state, you can expect the CO2 in the atmosphere to go up and down, and it clearly does. So if you're mathematically inclined and you want to make a simple system that has no physics in it really, but just sort of behaves like the real system, you can write the rate of change of the CO2 in the atmosphere is going to have a source term. So if volcanoes are the only thing that's going on, it's going to keep going up. And a sink term, which is related to the weathering reactions. And the sink term is dependent on the CO2 in the atmosphere, because as you raise the CO2 in the atmosphere, it increases the temperature and the acidity and everything. So usually, if you're lucky, you can solve this very simply. You can set this term to 0 and say that since the system adjusts on a short time scale and you're worried about the long time scale, you just set this to 0 and you solve for CO2, and you get the CO2 in the atmosphere basically is the ratio of the volcanic outgassing rate to the removal rate taken to the power 1 over this exponent. And that's kind of a simple way to think about how the Earth works. The problem is that the weathering thing here varies with time due to mountain building, and it varies with the solar luminosity. The volcanic emission rate also probably decreases during the age of the Earth, because the Earth was hotter earlier on and was cooled off. So the simplest application of this is that you pick numbers for the various parameters and the luminosity of the sun. This is the ratio of CO2 in the past to the CO2 today, and you pick a number n of about 0.25 for that exponent. And so as you go back to 4 billion years ago, you get CO2 about 1,000 times what it is today. Okay, so this is with the constant weathering term, but we know that actually continental drift cycles affect this weathering rate. So if you drive two continents together and form a mountain range, like for instance you're doing in Tibet today, in the Himalaya and all across southern Asia, the weathering and erosion rates in those areas are much higher than they are on the average planet. And consequently, you can increase K and you'll drive CO2 down. And in fact, there's a theory that the reason that we have ice ages now is because of the collision of India into Asia, which has raised these enormous mountain ranges, increased weathering. Not everybody agrees with that, but it's an interesting idea. Anyway, if you imagine that sometimes continents are colliding a lot, sometimes they're drifting apart and there's no collisions going on, you can figure that this K value is going to change on sort of hundreds of millions of years timescales. So if you just impose that on the model like a cycle, then you might expect that, to a very rough approximation, the history of CO2 on the Earth might look like this. It has its ups and downs, maybe by a factor of 10. But in general, it's been drifting down over the age of the Earth. Now, if we look at the last 600 million years, there's actually a few data points and a model that tries to capture this. So this, again, is this ratio of CO2 in the past atmosphere relative to today. It's 1 at the present. So the general idea is that if you go back a couple of 100 million years, it was probably 5 times what it is today. Back in the Carboniferous, which was when all that peat and coal was forming, there was a certain set of conditions where there was very natural but effective carbon sequestration going on. And the CO2 in the atmosphere was down around the present-day value. There were probably glaciations at that time. And then if you go back into the earlier Paleozoic, it looks like the CO2 values were much higher, 10 to 20 times what they are today. However, a higher CO2 back 500 million years ago of, say, 10 or 12 times, that would just about cancel out the difference in the solar luminosity between then and today. So if you wanted to keep the temperature constant, you would probably need an increasing CO2 that looks something like this. I didn't plot it on here. So the fact that these numbers are high back here doesn't really mean that it was super hot. It just means that it had to compensate for the solar luminosity. Here's another view of how the solar luminosity works. If you just don't worry about anything else other than how much CO2 you might need in the atmosphere to keep it as warm as it is today. This is the solar luminosity relative to today. I extended it out to 1. So this is where we are today with about 300 ppm CO2 and a surface temperature in the 280s somewhere. And if you want to go back to 4 billion years ago, to get the same surface temperature, you need the CO2 in the atmosphere to be something like 20 or 30%. Again, it didn't, because this atmosphere might not have been as oxidizing back then, some of that greenhouse effect could have been taken up by the presence of methane. Okay, so one other issue I want to squeeze in here is, so right now we're doing something extraordinary. There's been a few other times in the Earth's history that we know there have been extraordinarily fast releases of CO2 from the deep Earth into the atmosphere. This is a diagram that shows the stable isotope of oxygen, the composition of the oxygen isotopes in shells of foraminifera, which are marine organisms, particularly the ones that live at the bottom of the ocean. So these are what's called benthic foraminifera, which gives you an indication of the bottom water temperature in the oceans over time. So the temperature scale here corresponds to the data that are from 35 million years ago back. And so the warmest time in the last 65 million years was this area called the early Eocene and the late Paleocene, where the bottom water temperatures in the oceans were 10 or 12 degrees C. And there's this little spike here, which is called the Paleocene-Eocene thermal maximum. And it looks like in this period of time, for one reason or another, people think it might be release of methane hydrates rapidly. The CO2 in the atmosphere went up and the temperature of the oceans and the whole world went up pretty rapidly. So people have looked at this, and we're going to look at this in a minute. What's happened over the last 60 million years is the temperature of the bottom waters of the oceans have gone down pretty much to freezing. In some cases, they're actually below 0 because the salt in the ocean can keep it from freezing. And the first big ice sheet started to form about 35 million years ago as the temperature and presumably the CO2 concentration of the atmosphere came down. And then the northern hemisphere started getting ice sheets more recently. Let's go back and look at this peak here. Well, actually, one more thing. So what is the CO2 concentration that corresponds to that? This is an old diagram. I'm showing it because I did it. A student of mine, Sean McCauley, and I published this in a paper about 1990-something, 97 or something like that. So we took this oxygen isotope record. We sort of estimated what the global surface temperature might have been. We figured that you need a doubling of CO2 for every few degrees of temperature, and calculated what the CO2 concentrations would be. And you end up with concentrations of roughly 1,000 ppm back in this period of time. And the point at which the Antarctic ice sheet started to form was somewhere in here, when the concentrations in the atmosphere dropped below about 700 or 750 ppm. Okay, if you want to know how hot it was back then at that thermal maximum, these are estimated surface water temperatures for 55 million years ago. So around Antarctica, the temperatures were good swimming conditions, the same in the Arctic Ocean, and it was pretty warm near the equator, 35 degrees C for the surface ocean temperatures. Okay. All right, so now, quickly, we already talked a little bit about what's going on today. The emissions are 9 gigatons per year, and these are sort of net numbers that are shown here, but I want to talk a little bit about what that means and how big that number is. This is what it would be if it was natural. If it was natural, you'd only have the source of, instead of having all the CO2 from fossil fuel burning, you'd only have volcanism and other leakage. And this is what the normal situations have been for the last 50 million years since that last burp of CO2 in the Eocene. Okay. And, all right, so this is the way I think you should think about the Earth's carbon cycle and what we're doing at the moment. So there's a very rapid exchange of carbon between several parts of the Earth's surface system: the atmosphere, the terrestrial biosphere, terrestrial soils, and the surface ocean. If you add up the total amount of carbon here, it's almost 4,000 gigatons of carbon. The rates of exchange between them are in the range of 60 to 100 and some gigatons of carbon per year. So it's like the system is breathing all the time. There's a lot of exchange going in every direction. But if you draw a box around it, the total amount of carbon in this box doesn't change very fast. It changes very slowly over time. In fact, it's close to zero. Then there's this little bit of volcanic input, and this is usually compensated by deposition in the oceans, and then eventually it gets taken into the deep ocean. Okay, quickly, how do we know how fast carbon is moving around at the surface? Like, how do we know that carbon's being exchanged between all these surface reservoirs so fast? One thing, and Margaret Torn could give you a separate talk on this, and I hope she does someday, is that you can use carbon-14. So carbon-14 is produced by cosmic ray interactions in the atmosphere that produce neutrons, which then react with all that nitrogen in the atmosphere to produce carbon-14. And this carbon-14 gets mixed with all the carbon that's around on the surface of the Earth, the terrestrial biosphere, the surface ocean, the deep ocean, and soils and everything. And if you measure the atmospheric concentration of carbon-14 and relate it to the total, well, what you can measure is the carbon-14 to carbon-12 ratio in the atmosphere, and that tells you how much of the carbon-14 that's being produced by cosmic rays how much carbon is being mixed with that carbon-14 in order to produce the atmospheric composition. So what it turns out is, in order to account for this number, you need to have all of the carbon in all of the surface reservoirs, including most of the deep ocean, mixing with the atmospheric carbon on a time scale that's shorter than the mean life of carbon-14. So basically, on the time scale of 8,000 years, the carbon that's being produced by cosmic rays in the atmosphere is mixing with all of the surface carbon reservoirs. So we know that the mixing times have to be short in comparison to 8,000 years. There's other things the other interesting experiment that's been done by mankind was testing atomic and thermonuclear bombs in the late 50s and early 60s. Thermonuclear explosions produce a lot of neutrons, and the neutrons do the same thing that the cosmic rays do, and they produce a lot of carbon-14. So by the early mid-60s, the carbon-14 concentration in the atmosphere, or this 14 to 12 ratio, was driven up by about a factor of 2. And we've watched that shift back toward the modern value with time. So you can see that the time scale for returning this carbon to the original value is only about sort of 20 years. The radioactive decay time scale is 8,000 years. So this has nothing to do with radioactive decay. This is just that carbon in the atmosphere being stirred in with all the other carbon. So we know that there's very rapid exchange of carbon between the atmosphere and the oceans. And one other piece of information I'll show you, which is pretty old now, is people have done carbon isotope measurements of the deep water in the ocean to sort of determine if you look at deep water carbon, dissolved carbon, when was the last time that carbon was exposed to the atmosphere? It's sort of an age of that water. And the deep water in the northern Pacific is almost 2,000 years old. So this gives you a picture that the time it takes to stir carbon from the surface oceans and the atmosphere down into the deep ocean is a couple of thousand years. So these time scales are really determined pretty well by a lot of measurements that have been made. This has nothing to do with the bomb carbon, by the way, but in any case, we've got some information on those fluxes. So what have we done so far? Up until now, we've added about 500 gigatons of carbon to this upper system. And then, the main question is, how is it going to be distributed? And so right now, we know what's going on. About 45% of it is going into the atmosphere, 25% into the surface ocean, about 30% is going in to some combination of the terrestrial biosphere and soils. Okay? The big question is whether that's going to continue in the future, and the other question is how much total carbon are we going to add? By the way, if you compare the modern flux to the normal fluxes, this is what it looks like. So the width of these arrows are in proportion. This is the present 8.5 gigatons per year. This is the normal background, 0.15. Okay, this point I might skip, but the bottom line is when you look at the most extreme cases of rapid release of carbon to the atmosphere in the past, they pale in terms of rate in comparison to what we're doing now. This big event back here in the Eocene, 3,000 gigatons of carbon were released to the atmosphere in 6,000 years. That was a rate of 0.5 gigaton per year. So that's still like 20 times smaller than what we're doing now. Going from the glacial to the interglacial, that's trivial. A couple of hundreds of a gigaton of carbon per year was being transferred. The last point I'm going to make, and I'm going to not use all the slides, is that the big question is, what are we going to do in the next couple of hundred years? So this is release of carbon in gigatons per year versus time. So this shows the next 1,000 years. And the light gray line is if we're good, and the dark black line is if we're bad. So if we're good, we will start turning over our rate of emissions of carbon sometime late in this century, and by the end of the next century, we'll be back down close to zero. If we keep, this by the way is the modern trajectory that we're on up here. If we're bad and we keep burning carbon and essentially burn all the coal that we figure we can find, it'll look like this, and we'll put in 5,000 gigatons. It'll take us a few hundred years to do it. If we now look at a longer time scale, this comes from this paper by Archer and Brovkin, of about 10,000 years, the good scenario pumps the CO2 up to maybe 500 ppm, and then it comes back down to 400, and it gets stuck at about 400 for a long time because the ocean can't take it up anymore. If you do the bad scenario, it gets pushed up to almost 2,000 ppm. It comes back down to about 1,000, then it gets stuck there. And this is because the ocean has a limit in terms of how much it can take up quickly by neutralization of the acidity in the ocean. This is kind of shows what's going on in different mechanisms of taking up carbon. So it can suck up about, a lot of the carbon within hundreds of years, but then you end up having to redissolve calcium carbonate from the ocean floor to take up more. And in the long run, you have to wait for this weathering process on the continents, which takes forever. So a lot of this carbon that we pump in the near term is going to stay there. So in the good case, where we stick to 1,000 gigatons of carbon, this shows some more complicated models, different results for different models. But in the end, we come back down over about 500 years to 400 ppm, and we get stuck there. In the bad case, we come back down to about 1,000 ppm, and we get stuck there. This is the ice-free Earth level. In order to have an ice-free Earth, you'd have to melt all of the Antarctic ice. That's not easy to do. There's a lot of it. There's 3 times 10 to the 7 cubic kilometers of ice. Right at the moment, it's melting at the rate of about 150,000 cubic kilometers per year. So even if you doubled that rate, it would take 100,000 years to melt all this ice. So one good thing about Antarctica is it's a pretty good refrigerator. It will keep ice for a long period of time. So Greenland's not so good. And actually, the West Antarctic ice sheet is not so good. And I think Bill Collins and other people here are working on what might happen to the West Antarctic ice sheet. But this part of the ice sheet, which represents about 65 meters of sea level rise, is a pretty solid thing, we think. Maybe what they're going to find out is that you can destabilize this at the edges, and it could disappear at a much more rapid rate. This just shows this diagram to remind us about where we are with regard to total emissions. We'll hit about 500 gigatons in the next decade. If we continue on this trajectory, we'll get up to 1,500 gigatons or 2,000 gigatons by the end of the century. If we really do all these things, we'll keep it to 1,000 gigatons by the end of the century, and maybe keep the full integrated pulse that goes into the atmosphere down to maybe 1,500. Now, this is a diagram I got from George Moritas, who's been working on gas hydrates. And this shows all the carbon, shows all those different reservoirs. They have slightly different numbers than the ones I showed you. Here's the total recoverable and non-recoverable fossil fuels, 5,000 gigatons. That was what this number was based on, this diagram was based on here. But some people think that there might be at least that much gas hydrates, too. So if we're really bad, we'll get all that gas hydrate out and burn that, too. And that would mean that the worst case here is not even the worst case. It could be even worse. Okay. All right. So, again, what we're trying to do, I was going to talk a little bit more about this natural sink and the fact that we don't know what's going to happen in the future, but I'll just say that's the case without going through the details. This, of course, is our challenge to try to figure out how to go from where we are now with our current energy production and releasing 9 gigatons of carbon per year to producing 2 or 3 times more energy but releasing less than a third of the amount of carbon by the end of the century. And then this is the final thing. Some people are still confused about whether it's really fossil fuel burning that's the issue or it's some other thing. I think this is documented very well on the Global Carbon Project website. Back here in the 1960s, you could argue about it. Land use change was competing with fossil fuel burning, but that isn't the case anymore. It's mostly fossil fuel burning, and in fact, due to reforestation in the northern hemisphere, the land use change component has been going to 0. Okay, so this is what I want to leave you with. The major perturbation of the carbon cycle that we're doing is this idea of transferring carbon from the deep earth into the atmosphere. That was about, maybe it was 4 gigatons per year in 1960. It's now 9 gigatons per year or so in 2011, and it's going up rapidly. The current transfer rate is about 50 to 60 times greater than what's normal and what the normal sort of natural system is used to dealing with. So we're really stressing the system, and it's 20 times greater than even the most catastrophic release of carbon that's been observed in the geologic record over the last 65 million years. So finally, in my view, there's no question and there's no significant uncertainty in the size of mankind's contribution to the change in the carbon cycle. We're doing all of it. It's used to taking care of that 0.15 gigatons. All of the rest is due to us. Thank you.
We have question time for those of you who can stick around.
Janet. I can't see anything because of the, maybe I should stay over here if there's still going to be.
I have a couple of questions, actually. And one is about Antarctica. That's fascinating about how stable it is. And I'm more familiar with the Greenland situation, where you can have these sinkholes due to the precipitation of black, and it melts down, and then you start to get runoff underneath the mass of glacial of the ice. Wouldn't that also occur in Antarctica?
Well, if you want to answer that question, pass the mic over to Bill Collins and ask him what he thinks.
Yeah, the moulins have not been, I don't think those have been shown to be nearly as prominent in Antarctica as they are in Greenland. They are a problem in Greenland. And the lubrication of the ice base is really a big problem, because then you get, most of the ice loss in Greenland is dynamic, partly because of the lubrication of the base. So, yeah, we don't know, at the moment, Antarctica is much more of an unsolved problem. We don't even know the sign of the mass change for the Antarctic continent at this point. It could be positive, it could be negative in toto. So.
Did you have another question, Janet? Didn't you say you had two?
We'll come back.
In the worst case scenario, how much acidity does the ocean acquire? And will the ocean life be able to respond to that?
Is Jim Bishop here? Oh, okay. You know, I meant to look that up. There's been some work done by that. It's been on that done on that problem, and so some calculations have been done. I'm not sure that they've carried out those calculations for the length of time that's necessary to take this whole thing in, but it's possible that they have. It gets pretty acidic, I think, but I don't remember what the pH goes down to. Probably below 7. And then the issue becomes, how does that affect these carbonate shelled organisms that are really responsible for producing most of the calcium carbonate and eventually having it transported into the deep ocean. And there is a lot of work that's been done in that, but I haven't done my homework on that part of it recently. Bill, do you have, or is Margaret here? Do they, somebody else may be able. Somebody want to? Do you remember what those numbers are, Margaret?
My recollection is that the pH has been suppressed by a couple of decimal points. This, or is projected to go down even further by the end of the century. Yeah, the problem is that they've already shown, just by putting, they've already shown this effect just by taking seawater, subjecting it to a moderate change in pH and shaking it, that you can cause the shells of the organisms to dissolve. And so part of the problem is knocking out the bottom rung of the food chain. The other part of it is attacking the corals. So one thing that happens is that you knock out a lot of the phytoplankton. The other thing that happens is, that's a fairly robust projection, is that most of the corals in the world's oceans will go extinct, even with moderate levels of global warming, partly because of thermal stress and partly because of the acidification.
So one of the big uncertainties that I know Margaret could comment on is right now about 30% of the emissions are being taken up by the terrestrial biosphere and soils by some mechanism, and that's one of the things that we want to have as a future sort of developing lab initiative, actually, to understand that better. And we don't know whether that's going to continue through to the end of the century. Some of the models show that sort of turning around and the terrestrial carbon sink going to zero, and which means that a larger fraction of the CO2 that's emitted is going to be accumulating in the atmosphere, which means that more of it's going to be trying to dissolve in the ocean, and that will accelerate the pH change in the ocean. On the other hand, if we can keep that terrestrial biosphere sink active or expand it in some way, we could keep the oceans from having to respond so much. By the way, there's a science writer who's now looking for people to interview about geoengineering. Actually, I got an email from Jay Kiesling last night. So people are already starting to think, maybe we're never going to be able to avoid doing this. What are the mitigation and adaptation effects, or needs going to be? So The DOE, by the way, has not decided to dive into that yet. They've decided that it's not politically the right time yet. But it's not going to be too far in the future when that's going to be part of our research program, I think.
So when we look at the hosting out the carbon cycles, and we really only play with about 0.1% of the carbons available in the whole Earth. And so if you look back to about millions years back, and the temperature of the overall Earth surface is really well regulated, right, at this very narrow range. So why is that? I mean, there could be more CO2 coming out, and it could be at a much higher temperature, a much lower temperature. Why it's always at this very comfortable range for millions and millions of years?
Yeah. So some people view this feedback as being very tight, that it's very difficult to get the CO2 to go much beyond where it needs to keep the temperature in that range. But some people think that maybe that's a little bit too simple, and there's a lot of reasons to think that it's not so straightforward. In the simple model, the weathering rate is a very simple function of the atmospheric temperature and the pH of rain, which will go up as the CO2 comes up. But the fact is that it looks like, if you look at current weathering rates, they're not that directly related. To wherever you can sort of test this model, it has more to do with whether you have mountains and glaciations and you're grinding up rocks at a very rapid rate. Like glaciers do a real good job of powdering rocks, and then they wash that stuff out there, and it's very accessible to weathering because there's a lot of surface area. So exactly how that feedback works when you bring in the geology is a little mysterious. And it is possible that the temperature has wandered out of that range for periods of time that we don't pick up in the geologic record. I don't know if you paid attention to that slide where people have tried to estimate the paleo CO2 in the atmosphere. We haven't done a very good job of it. I mean, every one of the data points has huge uncertainties, and they don't agree with each other even in the same time ranges. And besides which, the time scale for adjustment to the system is about 50 to 100,000 years, even for the geologic part. And when you look back 100 million years, you can't tell. So you might get 1 point out of some soil that paleo soil that you can find. You get a number. You don't know whether that applies, for how much time that applies to. That may apply to one specific little point in time, and 500,000 years before that it could have been much different, and 500,000 years after it could have been much different. So there's a lot of work to do there, and I can still consider this to be one of the major geologic problems with regard to the climate system, is to understand what the variability in the past was and whether we can relate, determine cause and effect when we see the big changes. The Carboniferous itself is just, I think, absolutely fantastic thing where for almost 100 million years it looks like the CO2 concentration of the atmosphere was very low, and you were sequestering a lot of carbon in peat and coal and wood that wasn't getting broken down and returned to the atmosphere.
Can I ask my other one?
Sure.
So I was surprised that land use change didn't have that great an impact, and that it was actually going down a little, especially when one considers the amount of burning of tropical forests that's going on. That's encouraging. It surprises me, though.
Yeah, well, Margaret could maybe comment on that. I was a little bit surprised myself, but this is a fact that there's reforestation in the Northern Hemisphere.
It's also just the best estimate. Deforestation's been going down in Brazil because of policies, and deforestation is going up in Africa, but the net is that it seems to be going down, and that's mainly from satellite observations.
Yeah, so if you're interested in some of these numbers, the place to go is the Global Carbon Project website, GCP. And they They might even have more up-to-date numbers for 2011 or 2010 now. They should be coming out about this time of the year.
The 2010 budget was just released.
Yeah. This total volcanic release number also is a little squishy. We're pretty sure it's small, 0.1, 0.2. Maybe you can stretch it a little bit beyond that. But I've been trying to get Mac to think about how we can use helium isotopes to estimate that more precisely. But yeah. Well, is there another way to explain those numbers? The carbon numbers, they look really robust to me. That the carbon's been going in and out a lot.
Any other questions? Thank you, John.
You're welcome.